I'm Kodama in Riken. I will talk about evaluation of SPEC CPU and SPEC OMP on the A64FX. This is the outline of my talk. First, I will introduce the Fujitsu A64FX and describe its power management control such as boost mode, echo mode, and core retention. Next, I will summarize SPEC benchmark suite. Then I will show the result of SPEC benchmark on A64FX. After that, move to discussion and show the several analyses for the results, comparison by power mode, and number of threads. I have limited time, so I will skip about effect of SVE and compilers. Please refer the paper. Last, I will conclude my talk. Fugaku is the next-generation flagship supercomputer in Japan. Riken developed Fugaku along with Fujitsu. The public service of Fugaku started on March this year. Please show the information about Fugaku from this URL. Fugaku consists of 432 racks and totally over 150,000 nodes. The peak performance is lower than half exaflops in normal mode, but using boost mode, it becomes more than half exaflops. Fugaku took first place in multiple supercomputing rankings announced at ISC 2020, such as the Top 500, the HPCG, HPLAI, and Graph 500, and keep it 3 times in ISC 2021. The processor of Fugaku is the Fujitsu A64FX. It is ARM ISA processor and is the first processor to support SVE, Scalable Vector Extension. In A64FX, 2 SIMD pipelines of 512-bit are implemented. The A64FX is a many-core processor and consists of 48 compute cores, and internally, it is divided into 4 CMGs, core memory groups. That is a NUMA domain, and CMGs are connected by a bidirectional ring bus and support cache coherence between CMGs. A CMG consists of 12 compute core and assistant core, a shared L2 cache, and a memory controller. The assistant core is dedicated to OS operation, and its configuration is the same as that of a compute core. As for the main memory, 4 HBM2 stacks are installed in the CPU package. The capacity is 32 GB and the throughput is 1 TB per second on chip totally. Detailed microarchitecture is opened in this GitHub. The A64FX was designed for high energy efficiency using latest semiconductor process, that is TSMC N7 technology. Since it ran at the low power voltage possible, DVFS is not applicable. As a result, the prototype of Fugaku is ranked the number 1 in the Green 500 list at SC 2019. The energy efficiency is over 16 gigaflops per watt. Furthermore, to achieve even better energy efficiency in large-scale systems, various power control mechanisms have been implemented. Echo mode and core retention are introduced in next slide. It also supports boost mode, where it runs 2.2 GHz clock frequency. But since the power supply voltage should be increased, energy efficiency will be reduced. Since the frequency is common to all cores, it is not possible to set only a certain core to boost mode. The boost mode on the A64FX is statically controlled. This contrasts with Intel's Turbo Boost that is controlled dynamically. A64FX adopts several power knobs to reduce power consumption, keeping performance by controlling for each application. FLA only is one of the power knobs, which limits the use of one of two FPU. However, it became clear in evaluation during development that the FLA only alone may not reduce the power consumption. This is because of the standby power for stable operation by avoiding a large power fluctuation, and it does not change even if the power knob is controlled. Therefore, Echo mode is newly introduced, which is a mode that controls the standby power according to the maximum power when FLA only is applied. Core retention is another idle state, where eliminate standby power and reduce total power as low as possible. Echo mode and core retention can be set independently for each core. It is different from boost mode. SPEC is a famous benchmark suite for compute core computer systems. It was founded in 1988, more than 30 years ago. SPEC has many types of benchmarks. The performance of SPEC is indexed by ratio, which is relative performance compared to the reference machine, and the total index is the geometric mean of each benchmark ratio. For the general attribute of index, there are two types, base and peak. In base, all benchmarks use the same compiler option, while in peak, each benchmark can select the best options. And another attribute exists in SPEC CPU, speed and rate. Speed evaluates the single task performance where thread parallelism is possible, and rate evaluates the multitasking throughput. Here, base speed in SPEC CPU and base in SPEC OMP are only evaluated. First, I will summarize the execution environment for SPEC on A64FX. We use the Fujitsu compiler of this version and use Clang mode in C and C++ because it is better compatibility for open source programs. The optimization flags are shown here. We run benchmarks in normal mode of 2 GHz with setting of these environment variables. The first environment variable, paging policy, controls the timing of memory allocation. By default, memory allocation is performed when the program is loaded. For multi-threaded execution across multiple CMGs, it is necessary to set this variable to allocate on demand. That is the first policy. The second environment variable, arena lock type, controls the memory pool between threads. By default, a common memory pool is used between threads. When memory allocations are frequently requested within threads, it is necessary to set the variable to use independent memory pool for each thread. This is the result of SPEC CPU and SPEC OMP. Please show the detail in the paper. But roughly speaking, A64FX performance is less than a quarter of Xeon in SPEC CPU int, and 60% in SPEC CPU FP and SPEC OMP. In SPEC CPU int, almost benchmark run on single thread, and the single thread performance on Fugaku is lower because the frequency and the O3 resources are limited for the throughput-oriented architecture. In SPEC CPU FP, the performance of A64FX is lower than Xeon with the same number of cores, because core of A64FX is smaller than that of Xeon in O3 resources, and the area of the chip and the power consumption is less than half. Currently, the compiler cannot use SVE enough in many benchmarks in SPEC, and it is another reason, I think. In several benchmarks, A64FX performance is higher than Xeon, mainly due to the high memory bandwidth. Let's move to discussion. First, compare the power mode in which retention is disabled. The value in parentheses are relative value when normal is 100%. The power consumption shown here is the estimated power consumption obtained using the Power API on the node. Boost mode performance has improved by 11%, 9%, and 7% in SPEC CPU int, FP, and OMP respectively, and power has increased 9% in each case. The performance of Echo mode is the same as normal mode in SPEC CPU int, but it is reduced by 8% and in SPEC CPU FP and 4% in SPEC OMP. The performance degradation due to Echo mode differs for each benchmark. I will show the result of SPEC FP in the next slide. The left graph shows the performance of benchmark of SPEC CPU FP in each power mode. This benchmark reduces the performance about 25% in Echo mode, and these two benchmark reduces about 15%. They also reduces the performance in Boost Echo mode. But other benchmarks reduces the performance less than 10% in Echo mode, and they are recovered in Boost Echo mode. The right graph shows the power consumption of each benchmark. It shows that all benchmarks reduce the power about 20% in Echo mode and about 16% in Boost Echo mode. Programs that use a lot of FPU may reduce performance in Echo mode, but specific indicators are currently under consideration. Currently, it is better to evaluate once in Echo mode and use Echo mode if the performance does not reduce, and use Boost Echo mode if it is less than 10%, and use normal mode if it reduces further. Next, we compare the power mode where the retention is enabled. The values indicate the relative value to each power mode where retention is disabled. Performance is almost the same as when retention is disabled in each power mode. On the other hand, the power is reduced by 60% in the SPEC CPU int in the normal mode. This is because most of the benchmarks are executed by one core, so the remaining 47 cores are in the core retention state, and the power can be reduced. Even with SPEC CPU FP and SPEC OMP, where running 48 cores, a power reduction effect of about 18% and 8% in normal mode can be confirmed. This is because the transition to core retention is performed when thread becomes idle for 200 milliseconds or more, even during multi-thread execution. So I think the core retention is useful for reduced power with keeping performance. In SPEC OMP, 363 swim was 6 times faster than Xeon. We evaluated it by changing the number of threads to verify the effect of memory bandwidth. In this graph, the horizontal axis shows the number of threads, and the vertical axis shows the performance by ratio. The figure evaluates three types of thread scheduling: close, scatter, and balance. The close is the default setting, and the previous results are also the result using this. In close, threads are assigned in order from CMG 0. In close, the performance is saturated about once with 3 threads, because the memory throughput is limited in 1 CMG. And after 12 threads, the performance improved. The scatter assigns threads evenly to each CMG in round robin. The balance also assigns the thread evenly to each CMG, and it assigns them continuously within each CMG. In scatter and balance, the performance improves up to 12 threads, but after 24 threads, the performance gradually decreases. The maximum performance is at 24 threads in balance, which is 11% higher than at 48 threads. In this way, performance can be improved by optimizing the number of threads and thread scheduling according to the application. However, such optimization for each benchmark is not allowed for base in SPEC benchmark, and it is necessary to show the score as peak. Because there are cores that are not used, it can be expected to have a power reduction effect due to retention. Therefore, we compared each power mode when the number of threads was changed using balance. The upper graph shows the performance in each power mode. It shows that the performance is almost the same with the power mode. The lower graph shows the energy efficiency represented by 1 by energy. It shows that 16 thread with echo retention is the most efficient. The performance is 6% higher, and energy efficiency is 60% higher than normal with 48 threads. Optimizing the number of threads and the power mode can reduce power while improving performance. I will conclude my talk. A64FX was evaluated using the SPEC CPU and SPEC OMP benchmarks. The performance of A64FX in SPEC CPU was lower than Xeon with the same number of cores. That in SPEC OMP was also lower than Xeon with the same number of threads. But several benchmarks greatly exceed Xeon thanks to high memory throughput. Comparison using A64FX power mode. By enabling core retention, power can be reduced without affecting performance when there are unused cores. Even when all cores are used, the effect of power reduction can be expected if there are threads waiting to synchronization. In echo mode, all benchmarks can reduce power consumption, but several benchmarks reduce performance, so it is necessary to understand the characteristics of program. Comparison with varying number of threads, the performance is saturated when the number of threads increases in memory-bound programs. In that case, performance and energy efficiency can be improved by executing with an appropriate number of threads, thread scheduling, and power mode. We would like to optimize for each benchmarks and consider general optimization guidelines. Thank you for attention.